Good morning, everybody. Welcome to our International Physics webinar. Today it's our 261 International Physics webinar. We have with us here today Dr. Jiandi Zhang, sir, Professor of Physics, Department of Physics and Astronomy, Louisiana State University, USA. He's already connected with us from Beijing, China. So, sir, welcome to our webinar, and thanks for joining with us, and thanks for accepting our invitation. So dear student and viewers, I think you have already come to know the title of this today's International Physics survey. Title is the exploration of emergent interface quantum state of correlated electron materials. And I think you will enjoy this session, and you can ask question by commenting, and you can join with us using this link. So sir, it's your time. You can start your session.
All right. So I'm going to start it now. Okay. Can you hear me, everybody?
Yes, everybody can hear you.
Okay. So again, thank you. I'm really. It's very great to seeing you guys on online. But my as you know, I am a experimental condensed matter physicist. Actually, the last fall, I moved from Louisiana State University to Beijing, China, in the Institute of Physics, Chinese Academy of Science. So I'm now a professor over here. Okay, so today I'd like to give you some flavor, some very basic kind of introduction about what we are doing, and particularly about exploring the interface quantum states. Now, certainly you have to, how to create those interface is a big issue, and then you try to characterize those new state existing interface, and eventually try to understand. And certainly, I try to give you an idea. So basically, interface is the device, because any devices, any electronic devices, is come from interface. All right, so maybe a little bit long outlines, but I think I will try to squeeze my talk, at least within maybe 45 to 50 minutes. All right, so basically I wanted to tell you a little bit, what is condensed matter and what is condensed matter physics, starting from there, and then to look back in last 30 years, maybe more than 30, 40 years, what is going on in condensed matter physics. Okay, in particular, talking about what is the evolution of science in condensed matter, and what is possible, I think, is the revolution in condensed matter. And then I'm going to go back, say, okay, compared to before, 40 years ago or now, there's a lot of change. In particularly, people starting from simple material to complex material. And then, another thing is why complex material? And then what kind of tunability we can have to change the property of material. In particular, I'm going to focus, switch my gear from bulk crystal to artificial structure. And this is what I have been doing for many years. All right. So basically, it's try to using our knowledge to make something impossible possible. Okay. So this is all the new stuff coming, I think, in condensed matter physics. All right. So from here, I just give you a small chat. What is condensed matter physics? It's certainly including hard material, soft material, and then look at the crystalline material or non-crystalline material, and then to look at their property. I'm not quite familiar in the soft matter, and kind of have a liquid crystal. I have different kind of even biomatter. But we realize as a system of condensed matter, it got to have a lot of atoms in there, and they form a different kind of structure. And you try to dig out all kind of property. So the atom is different, completely different from, for example, many people working in nuclear physics or particle physics. They are looking for individual particles. but we are looking is a sample of many particles. For example, typically you can say it's 10 to the 23rd of ions, and maybe it's more than 10 to the 23rd of the electrons. All right. And because every atom can carry many electrons in there too. All right. But one thing is for sure, the condensed matter physics is trying to deal with either macroscopic or microscopic physical property of matter. And again, those matter has many particles in there, but especially in the solid or liquid phases. And those phases which arise from simply just electromagnetic forces. Okay, so certainly from particle physics point of view, we thought, condensed matter people is only dealing with the electromagnetic forces, which is we're not. But the most exciting things is using this kind of interaction and try to assemble many particles together and to see their collective behavior. And I think that's the most important thing for the condensed matter physics. All right. So now, in the last many years, there's a lot of the interesting condensed matter physics going on. All right. And I like to think about it is look at from those all kind of discoveries. And there's two categories I like to talk about. The first thing is talk about it is simply you have evolution in the understanding of condensed matter. And the other one, you do really have the revolution. And I'd like to give you some example. For example, like here, we are talking about light. And you take a candle and you put light on. And this is certainly the importance is obvious. And it is technological things. And now you say, okay, we can make a new way to have the light. That's, I'm sure, lantern is one of it. Okay, so the good things for lantern compared to candlelight is, you have a shielding, so we are not afraid of the wind to blow it off. All right, but this is nothing but evolution. You still using the light, right? Well, this is a revolution. You compare to the candlelight as well, compared to the electrical light bulb created light is fundamentally different. So this is what we call revolution. And if you want to keep going, if you're using simply the tungsten wire inside the light bulb to light it up, then now we have LED to do it. And it is fundamentally different in mechanism. And I thought this is also another revolution. All right, so from that point of view, if you look at it back, in, for example, 2009, and there's a Nobel Prize, awarded to, again, I can categorize them as in the field of condensed matter. All right, this is for the groundbreaking achievement concerning the transmission of the light in fibers for optical communication. All right, this is exactly the CCD sensor. And those three gentlemen, they share the Nobel Prize. But I thought this kind, the basic physics is there. They're using this and they created the CCD sensor. And this, even though they get the Nobel Prize, but I think this is evolution in science, not really necessary to be revolution. But it is very important to our technology application. Now, and I thought this is completely different. Let's go even further back. Right, this is 1956 Nobel Prize. Again, is for the communication, but it is for their research in the semiconductors in their discovery of transistor effect. You know, this is go back to 1904, people using the vacuum tube try to amplify the signal, right, in the telecommunication. And then until this vacuum tube is being used for a while, until 1954, this is the first transistor has discovered and using semiconductor material. And I'm sure now you all know it's called PNP or those MPN, those junction. It's related to the interface. And using different doping way of the semiconductor, we can create an interface, you know, behavior, which is fundamentally different from the bulk one and allow you to give this kind of transistor effect. And those three gentlemen, Badin, Shockley, and Brayton, they three shared the Nobel Prize in 1956. So I thought this is a revolution because completely you change the mechanism for doing so. All right. So I'm sure now I'm likely to talk about, certainly, if you talk about condensed matter physics, you cannot avoid to talk about the superconductivity. So, you know, the superconductivity was discovered in 1911 by Onnes, all right? And just look at the mercury, suddenly when you cool it down low enough, the resistivity goes away. And eventually people find out this is so-called superconducting behavior. Now, I want to talk about it as another, I thought is also a revolutionary type. Nobody think ceramics material can become superconductor because usually ceramic material or oxide, we use that one as an insulating, you know, material, right? So never can think it is conducting or even it is superconducting. And these two guys, they discovered in 1986, right, a kind of so-called copper oxide and become a superconductor. Now, even though the transition temperature is about 36, 37 or around that Kelvin, all right. But now we realize we can have more than 100 Kelvin of this class of superconductors. And this discovery is certainly another revolutionized discovery, right? It's definitely is revolutionary, all right? Now, the final one I wanted to give the example related to those discovery is 2007 with some kind for the Nobel Prize, even though the discovery is only in 86, 87, all right? But the prize is given in 2007 is for the discovery of giant magnetoresistance, all right, by these two gentlemen, Ferd and Grunberg. All right, this is actually, I'm sure, I don't know how many people you using the cell phone, but your readout is already using this kind of idea. All right, when you can create sandwich of two different kind of material. One is a magnetic metal, and the other one is a normal metal, like a copper or silver or gold, and put them together within the nanometer scale, and they find out the transport, the conductance go across those interfaces. It really depends upon how the magnetic property or magnetic ordering relatively happening between two layers of this sandwich. Okay, so this is create a so-called giant magnetoresistance. With this kind of discovery, after 10 years, I mean, Apple or many other companies already using this kind of setup for the market, for the cell phone. All right. So again, this is another thing I thought is interesting and also important through the designing of material to the discovery and then eventually to the marketplace. All right. Any question? Okay, I thought I have given you enough example, but I just couldn't stop to talk about this. Another one is 2010, the discovery of the graphene. And I think this is from the how to make a graphene is not that difficult. But the most important, by these two gentlemen, they find out, okay, there's a lot of interesting property of the graphene. We know the most important, the electrons in the collective behavior in this material is actually can only be described by relativistic theory. Okay, solid state is not using Schrodinger equation. You have to use Dirac equation to describe this kind of behavior. And I thought that's, again, is another design into discovery. But it is the discovery maybe in the next few years or maybe longer to find a certain application in the market. Okay, so if you go back, this kind of from the time evolution, and then we see all kind of different evolution in advance of the condensed matter or revolution type discovery in condensed matter. Here I give you kind of a check to see what is happening since 1970s, maybe the end of 70s. All right, we find out all kind of interesting physics in condensed matter, and I'm sure is really exciting time right now. Okay, so basically you can have so-called a fractional quantum Hall effect, a way different from the integer quantum Hall effect, and in heavy fermion behavior in real Earth related high temperature superconductivity, as we just talked about. Colossal magneto resistance is beyond the giant magneto resistance. All right, and certainly in the last maybe 15 years, people starting to talk about the multiferrics and the quantum criticality, Dirac fermion behavior, like we're talking about in graphene, and then evolve into topological insulators. All right, and certainly a very important issue now is wire semimetals. So those are related to the many electrons or atoms in the solid. And even though the fundamental interaction is nothing but electromagnetic, but in symbol or the collection of those atoms within their collective behavior is fundamentally different. It's different beyond individual atoms. And this is, I'm going to elaborate a little bit more. And the other things is certainly you have the nanomaterial development, right? You have a low dimensional material. And so I think in the last 40 years, this is two directions, and they certainly entangled together to form a new platform for the condensed matter physics. All right. So if you go back again, if you talk about the very simple like transistor cases, we cannot avoid to talk about a semiconductor, and very simple semiconductor like a silicon. And you can make all kind of semiconductor-based technology, like nowadays we are using. And the basic things we realize is it is quite a simple material. You just stop a little bit. And the most important, for example, this is a silicon age. And the most important is the p-n junction, which I just told you is create an interface. You interface between p-type semiconductor and n-type semiconductor. Right at interface, you build up a new behavior right at the interface, and you create a diode character. And I thought this is the old age science. All right, but I also tell you the interface is the device. Now, when I talk about it, the new development, and I thought it could be the development in 21st century, which is I call it a complexity error. Is the error we are going to get into a much more complex material. certainly complex material, you create a lot of difficulty, I will mention about it, but at the same time, it gives you a lot of interesting property as well as, if we understand it, tunability. So the new material, the very important one, I'm sure you know that this complex material contain 5 different kind of elements: mercury, barium, calcium, and copper oxide. This is a kind of layered compound, and there's a sheet of the copper oxygen sheet. And this is exactly people talking about the material, the ceramic material, which you have highest transition temperature for superconductivity in cuprate. Again, you can reduce the dimensionality to create a single sheet. And then you can create a single sheet like a graphene. Or we can create a little bit of a quasi-single sheet, like those transition metal that Chuck coordinates, all right? And like I show over here. And they involve different elements in those compounds, either crystalline, like we just talking about, and they create a lot of interesting or emergent property, which allow us to explore, right? So the theme is like this. You come from very simple atom, and I'm sure you thought you understand those simple atoms. For example, take any atoms, even though, certainly the simplest one, like hydrogen, just 1 electron surrounded, and we already know what is going on in very detail. Then or even you take a carbon. But now if I take those carbon and put it into a little bit more complex structure, and I'm sure many of you know that, like a molecule of the C60, the carbon 60. All right? With that structure, and there's a lot of new property comes up. Certainly very symmetric, but it's a 5-fold of those structure in there. And the most exciting people not only just discover the interesting property of the C60, carbon 60, but you put a certain doping. Excuse me. For example, put a 3 sodium or potassium atom in there, and each atom over there has 1 s electron in the alkaline metal, and they can create a superconductivity up to 36 Kelvin by doping. So I think it's when you get more and more complex, certainly like a cuprate, and even though the structures are getting more complicated, while the physical property is much more interesting. All right, so I will try to give you a tune. The very important things, for example, the superconductivity for the C60 is beyond each individual carbon can create. And certainly for the superconductivity in cuprate is also beyond each individual building block of this material can have. So what I try to give you a conclusion is that we used to think that, it's not me actually, Sir Identon. We used to think that if we knew 1, we knew 2, because 1 + 1 = 2, right? We are finding now that we must learn a deal more about the so-called n. 1 and a 1 are 2, but that n can be different. What I'm trying to say is maybe 1 + 1 could be larger than 2. Exactly of those emergent phenomena is actually different. It is coming from kind of collective behavior rather than individual building block, the behavior from them. All right. So with that tone, I'm trying to say, okay, so in the modern condensed matter, and we are looking for many, many emergent phenomena. And they are the properties of a system of many, many interacting parts that are not property of the individual microscopic constituents. All right, not an individual particle or element can create that. All right, so very simple. You go to the ocean, go deep into the ocean, you see the fish grouping. Each of the fish, they don't know they can have this kind of assemble of the structure. But when they put them together, they look like that. All right? So actually, if you understand this already, think about that. And basically, in each levels of complexity, that could have an entire new property appears. And they certainly are equally important, right? From fundamental science point of view. And this is actually the driving force for me, for many of that. So, for example, we are talking about superconductivity, and I think you can see this picture in this video in the website, and so to tell you what is interesting. But actually, the superconductivity itself, it is a collective behavior. All right, it is the collective, right, of because of the Cooper pair, you change all those family of the fermions into boson, and they form a pair which we call Cooper pair in such a coherent way in condensate, and eventually they can travel without scattering and to form a material which without resistivity. All right, so that's one of the very simple things. It's a complex behavior. Okay, I'm going to skip this. It just tell you how the development in the last maybe many years after the discovery of the superconductivity, there's different class of superconductivity comes up. And it's all related to when the making the material even more and more complex, you have a tunability, you can tune this kind of collective behavior to a higher temperature. All right. So again, I skip this one. Is basically I want to tell you the system which has a complex emergent phenomena is normally should be coming out from, right, complex interactions, which is between all kind of neighboring electrons. All right. And so you cannot using so-called single particle picture to understand it. Okay, so I think that's one of the problem we have. It's also give us very profound challenges in condensed matter physics. All right, so now, so it seems you realize, yeah, if I make the material very complex, I can have all kind of interesting behavior. But why should I? And if I do that, what is interesting? You compare to the basically the simple, very simple silicon. You have semiconductor, you can create a device, but up to now, we only deal with charge in semiconductor industry. You dope it, you have not much of tunability you can do. What I try to tell you, even though those complex material is complicated, but it gives us a new tunability. You can change the dimensionality, you can change doping carriers by varying ionic size because you put a different the element in there create different ions, or you can even create a surface or interface. And so that on the surface or at interface, the physical property can be completely different from their corresponding bulk material. And this is great. Okay. So I'm going to talk about more of them is the interface. All right. So why interface? Take a piece of bread. It's very good. If you're hungry, you say, give me a piece of bread. Great. But you say, I can do this. If I make a sandwich, it could be much better taste, right? And much better nutrition too, more nutrition at least. So I take a metal and I try to measure the conductivity or resistivity, right, with or without a magnetic field. And you will find out the change of the resistivity for a metal, take a very normal metal, for example, is maybe about 2%. Okay? If we make a sandwich, like we just taught you, in this giant magnetic material multi-layer, and I created two interfaces, like a copper, like here I put a showing of this schematic view. take a magnetic cobalt and take a normal, just simple metal, a copper, and another cobalt, and then I put this kind of connection, and I apply magnetic field. I can create an on and off switch, and the magneto resistance can change to like 200%. And this is exactly is being applied in modern technology, and tell you how, if we can artificially to create those interfaces, it will help you to extend the functionality of the material, or even the new material, new functionality. All right. So again, I show you this before. I say, no, I can even make a more complex compound, right? Like this, right? This is a perovskite material, contains a rare earth and alkali metal element in the kind of manganite, manganese oxide. Okay, and very interesting, this material, if I without apply any external field, if I only cool it down from room temperature here, and the room temperature is sort of the metal, and then you look at this resistivity as a function of the temperature. So let's start it from the room temperature, and I cool it down this material gradually, and they turn about, right, 275 is a sudden drop of the resistivity and become a very good metal. But when you cool it about 140, and this material turn into a very large resistance and eventually look like an insulator. This is one of, just take those piece of compound, but it's different from the metal, different from the semiconductor, because it's such a complicated behavior for different phases. And now, even interesting, say suppose in this low temperature range, if I apply a large enough magnetic field, and find out, my God, the resistivity the phase can change from the insulating one to a metallic one. And this is not just giant magneto resistant behavior. It's actually can turn the insulating state to a metallic state. So this is so-called field-induced coupled metal insulator transition in the magnetic phase transition. Because when in the insulating phase, the system is anti-ferromagnetic. It means your spin near my spin, the anti-parallel. And when you apply enough field, you turn into a ferromagnetic metal. Okay? From an anti-ferromagnetic insulator to a ferromagnetic metal. So it's a coupled electronic and magnetic transition, simply by applying a giant field in there. This is similar to this one, the switching behavior of the magneto resistance. The only difference is now the magneto resistance change can be very, very big. So the complexity is give you also the opportunity to the tunability. So I think I have already talked quite a while. So in the last few, maybe 15 minutes, and I'm going to talk about what I'm doing. So basically, we try to follow the theme I'm talking about, and we try to create either intrinsic interface behavior, like we talk about the complex layer compound, or artificial structured material. The things is, if we create like those heterostructure, and then the interface has completely different behavior from their individual bulk. And this is what we want to talk. And we wanted to using interface because it's broken the symmetry. And we wanted to use interface to perturb the dedicated coupling of different degree of freedom in those complex material, and to obtain or explore the new property near the interface. And that's exactly the point we are doing right now, right? And I think this is important, and because eventually any kind of application of those new complex material, you need to deal with interface. Okay, so one way to do that is being actually Harold Huang and those guys in long time ago in 2000, beginning of this century, people can using advanced technique to grow different kind of atomic resolved artificial structure. For example, people can grow the strontium titanite. Okay, it's one of the pros guy with lanthanum titanite, and they can form a very interesting property because both material are insulator. One is, we call it, is band insulator, and the other one is, the other one is the so-called mud insulator. But they find out if you have those interface over there, and you can have a metallic behavior right in the interface, so-called 2D electron gas. And even interesting, I give one more example. Instead of the lanthanum titanite interface with strontium titanite, I using lanthanum alumini. So lanthanum alumini is again is an insulator. Strontium titanite is also an insulator, and I can create this kind of beautiful interface, and even the interface becomes superconductor. And superconductor, even though the temperature of transition temperature is very lower, but conceptually is revolutionized, right? So the interface between two insulator oxide can have the superconductivity, right? This has created a lot of the interest in complex material study, right? So to do those kind of things, in particular, you try to understand. The most important is to try to figure out what is the structural composition and property relationship. We could have an interesting property or behavior right in interface, but you want to know what is the origin of it. And to do so, the most important is that depends on how good you can create a sample. For example, this is we have done it, a lanthanum nickelite on strontium titanite. It's beautiful, beautiful interface. You almost see basically just a beautiful extension of the crystal. This is a TEM image, all right? So to understand the interface property, you definitely need a combined advanced growth as well as a comprehensive characterization, and got to be atomic precision and allow you to really dig out what is a microscopic nature for those observed behavior. This is what I have in Louisiana, and unfortunately now this system has left it to somebody. I don't know. A new faculty member, we take over of that, but I'm going to build up the new one over here in China, even a better one. And with this system, you can have a growth system. You can have all kinds of characterized, and I don't have time to go all through it. Now, if you have money and you're smart enough, you can do it. All right. And I'm sure in the future of you guys, you should be doing even much better. All right. So I will skip this one just to show you. This is to tell you how we study those complex material, and starting from the material growth and using the advanced microscopy, for example, like using the TEM, the scanning transmission electron microscope to do it. But I just want to jump to two interesting things I want to talk about. And this is taking me maybe 5 minutes. I can do it 5 minutes. In two examples. One example is I want to grow an interface to create a so-called interface-induced magnetic polar metal. All right. And I put the two material. One material is called BTO, the barium titanite. It's one of the oxide. and sandwiched, right, with strontium leucinide. In the bulk material, strontium leucinide is metal. Okay, so that's one way. And the barium titanite is a polar insulator. Okay, it's ferroelectrical material. Then the second example is I can do it, just insert one layer of material, one layer of atoms into this kind of the 3D cross-section view into the calcium leucinide, which is a cousin of the strontium leucinide. And this is created very, very different behavior. And we are just submitting this paper, all right? And this one has been published in Nature Communication. So you need to have a very, very good way to grow those material and with atomic shape of the interface. And those are the people who doing those real job. I didn't do it, they do it, and I just help him to understand it, maybe. All right. So basically the first things I want to tell you, and usually a metal cannot be polar. Okay. Polar means I have a dipole in the material. But if it's metallic, and the free electron immediately to screen out those polarity, and eventually everything is neutralized, and there's no polar at all. And usually this is what we learn in the general physics. But Anderson point out sometimes you could have that under certain condition, and we did it. So let me just go quickly. So we grow this. I told you the BTO, barium titanite, is a ferroelectrical insulator, right? While strontium leucinide is a magnetic metal. Both are perovskite. The only difference is this strontium barium titanite has a polar structure. So they can have a polarity in the vertical directions, and the strontium leucinide is just an orthorhombic structure. It's a ferromagnetic metal. All the spin, all the magnetic moment in the ruthenium is likely to line up also perpendicular direction. All right. So what do? We grow this material, and now it's grow this way. Okay, let's look at this way. Okay, so this is my substrate using strontium titanite, and I grow a 9 unit cell of the barium titanite, and then I grow a 3 unit cell of the strontium leucinide, and then I grow another 10 or 9 layer of the barium titanite. And the purpose is I using the barium titanite create a polar structure, try to influence the strontium leucinide. And at the same time, I want to maintain the strontium leucinide property? And this is what we are doing. So we find out it's actually in the strontium leucinide, they do have the polar character because the ruthenium atom is moving in one direction while the oxygen moving in the other. And that's you create an internal dipole moment. And this is followed because of the barium titanite has the similar kind of the moment or displacement of the atom. Okay, so you can find out the detailed displacement of those atoms. So suppose I create this kind of polar displacement in this strontium leucinide layer, very thin layer. All right. So now what is the property of this strontium thin layer? You create this sandwich, and if I only have 3 layers of the strontium leucinide as a film, the magnetization is like this. There's no magnetic property at all. All right. So if I make the sandwich, and you definitely has a magnetization. And the Curie temperature is about 130 around here. Okay, so this is amazing. The only thing you did is you put this 9 layer of the barium, 10 layer up, 9 layer bottom, and 10 layer top, and sandwich this 3 layer of the strontium leucinide. Then the magnetic properties comes out. First, second, look at the detail of that. And you find out this is because not only you create this magnetic layer, but you also change microscopic and electronic structure inside of this strontium leucinate. It's actually turn the leucinium, this so-called low spin state to the high spin state. Okay, so all the spin in each orbital of the electrons, they line up perfect together. All right. So once we look at that magnetic property really can enhance, and look at if it is a metal or not. So if I only grow, again, only just a 3 layer of the strontium leucinate, it is an insulator. Okay, this is resistivity as function of temperature. It is an insulator. While if I put, again, this sandwich, it turned into a metallic behavior. So again, it's showing you exactly what's going on. And you can also look the magnetic resistance. The characteristic of butterfly of the behavior tell you it is a ferromagnetic in the ground state. So we use one stone, shoot for 2 birds. All right? We enhance the magnetic property by doing this kind of artificial structure and give into a change into metallic there. In the same time, we polarize it. So from artificial structure, we really can make this happen and make it a so-called artificial magnetic polar metal. And this result is published already. I think I have to stop here because I think we have already over the time. Okay, so I'm going to maybe not talk about this kind of another subject. I want to go directly and just show you another example we have done. And we have beautifully to manipulate those in a talking layer structure and find the exciting property in there. All right, so I'm going to skip this one and directly to acknowledge many of my colleague contribution. I'm not going to all go into in details. And many of them you need you need not only you have the growth people, we need a characterization in different way the people and the people to help and to make this happen. So finally, I want to end up this picture. This is also we have done it before, and I want to end up this one to tell you there's a lot of interesting things we can do in condensed matter physics, and I try to convince maybe some of you are like to do this field, and sky is your limit. Thank you.
Yeah, thank you, sir, for your wonderful presentation. So we have got question. So if you allow, you
So
can
I'm going to, I'm going to look at the. Now let me see. I need to go back to the page so I can see those questions. All right.
The question is what is really meant by strongly correlated?
Okay, good. Now think about it. If I look at the semiconductor, you still or metal, take a piece of gold or copper, and in principle, or even the material we are talking about, like a high temperature superconductor, you have many electrons, and if we squeeze those electrons together, certainly electron, you have a 2-body interaction, you have more than 2-body interaction, we call it many body. So the strong correlated, what that means, it means if I change one of the, say like a position of one electron and the other electron then responds in the correlated way, in very strong correlated way. It means you cannot just using a single particle picture to describe it. All right. So give me just a more professional language to say that if I consider semiconductor or simple metal, even though it's many electrons, but I can using the interaction to one of the electron using equivalently using a potential to describe it. And this is so-called the local density functional theory to do so and allow us to do all kind of band structural calculation. However, in the strong correlated electron material, you cannot do that. So you cannot using quasi-particle, or you cannot use the single particle picture to describe it. And this is what we talk about it. And the reason is because the electron-electron interaction is so strong, they really build up the many-body interactions in there.
Sir, thank you for your discussion session also. So as the video will stay remain in Facebook and YouTube, so anybody can ask question later also. And if I'll get any question, then I'll inform you. So thanks again.
All right.
It's a
Very
pleasure
nice.
to host you, sir.
Okay.
Yeah,
So yeah. Thank you. So I hope maybe some of our students like to be in the field of condensed matter.
Yeah.
You can apply the graduate school here, or you can apply graduate school somewhere else, including the US. All right. Welcome.
Okay. So yeah. Thank you. So if any of our students want to study in your group in Beijing, China, so what is the procedure for application? So currently maybe you are not taking international student due to COVID.
For many, you can certainly in our website. You go to IOP, AC of China, and you just type in Google and just type in Institute of Physics, Chinese Academy of Science. You see the website, and there's the English version of the website, so you can go to apply. And they have online application too. All right. But if anybody really interesting, certainly let me know. I can help too. All right.
Okay. So they can directly send you mail also.
Certainly. Yeah.
Yeah. So and that will be great for our student also. So thanks, sir, for everything, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. And hopefully, when the situation become better, I'll invite you in my university and my beautiful country, the face-to-face session. That will be wonderful for us also. So
great. So we keep in touch. Okay.
Bye.
All right.